will not able to get the defined output in a single layer. Okay, yes, we are going to see on application. Okay, they are adding some readings. The readings applied, we are going to apply the single layer and value multi-layer, and we are going to make a comparison single layer, multi-layer. Okay, we are going to see. Anyway, first you can observe it. What is the single layer is? Yes, input layer is the output layer is there. If the layer is going increasing, yes, you can able to get output, but it is not a different output. Again, right now, again, if you are going on rearranging the weights, it's possible, but it takes more time. What happens? If you have some intermediate layers, as the middle layer, what happens? Yes, the middle layers will contribute. For example, if I want to relocate the weights, if I want to relocate the weights, okay, I want to relocate all the weights. If you have some middle layers, as like the multi-layer, if you have some middle layers, okay, as like this, what happens? Okay, yeah, for example, first we can relocate that weights. We can relocate this weights and we get the different output no problem. For example, we can if you want to get the different output here, yes, we have to relocate the weights here, but we have one more layer inside means what happens if we slightly adjust with respect to the middle layers, yes, if we get the different output, we can leave it as it is. Okay, what happens if middle layer plays a tedious role, okay, to minimize the time consumption. If you have a single layer, means what happens if you are not able to get the different output, you carry on, okay? Still you have to continue so many works to relocate the weights. But here is not like that, okay? What I said that, yes, we are forming duplicate neurons. Yes, we are forming some duplicate neurons. That neurons, what happens, will reduce, okay? But will reduce the work of the single layer and parallelly improves the efficiency when combined to single layer. Okay? These second layers are some neurons. Yes. So what I said that we can able to increase the neurons here. Here this is fixed and this is fixed. But here we can assume it. So for example, he is doing 8 neurons. He is making attempt, okay, with 8 neurons. He is making attempt with single neuron, 6 neurons. So he is making attempt with 9 neurons. What happens? Yes, we can able to get the results. Okay, and you can able to check the error. Okay, for 6 neurons, error is minimized. For 8 neurons, error is 2 minimized. For 10 neurons, error is very low. Okay, so another neurons, how many neurons is going and increasing the hidden layer, what happens? It's okay, it's how many layers going and increasing the layer, it improves the efficiency of your work. If you're doing the real-time system in the MATLAB. Okay, what happens is single layer is nothing but it is hidden neurons. Okay, it will play back the architecture to improve your efficiency. Okay. Okay, sir. So that is what here. It is formed by interconnection of several layers. Yes, we have several layers and parallel. Input layer is this input and buffers input signal, and output layer generated output. Okay, the layer between the input and output is called hidden layer. Hidden layers located in between these two layers. 0 to certain layers you can vary. You can vary 0 to several layers. Okay, another neuron is going increasing. Yes. What happens? Another neuron is going increasing, the efficiency will be increased. But that should limit. Okay, one little layer is there. You are forming some duplicate neurons. For example, this is forming around 8 neurons, this is forming around 9 neurons. Okay, that should be limited on little layer. For example, that should be around 12 neurons. If you are going and increasing more than 12 neurons in a single hidden layer, sorry sir, if you try to make an attempt with 30 neurons, again what will happens? The graph will goes up and again it comes down. Okay, in LLP, what happens? LLP, if you make an attempt with 0 neurons, what happens? Error should be like this. And parallel, what happens? If you make 5 neurons, error becomes like this. And again, 12 neurons, error will be like this. And again, if you go in this means error will be strengthened. That is, error will be increased. Okay, what happens? Go on 13, yes, error will be increased. Okay, graph will go up and down. Okay, that's a thing. Here, the output layers. 0 to 7 layers network, and more the hidden layer, more is a complex error, but efficient output is pretty. Think of it. More the hidden layer. Yes, going into this hidden layer. Yes, increasing. More is a complex layer. Increases a more complex. Your work is too tedious, but you are not going to do any work. Software is going to do work. Okay. Since if you are auto-building, yes, I am tedious. So you can think of it. It's tedious process. Sorry boss, I cannot able to make 8 neurons, 6 neurons. I can stop with 2 neurons. It's more than enough. Even the others getting a lot. They can stop with 2 neurons. But so software building, why you not able to increase around 10 or 12 neurons and try to increase some hidden layers. Okay, hidden layers. Yes, you can get the efficient output. That's the major thing. Okay, that's the efficient output. Okay, sir. Next one is feedback. That's feedback networks are different networks. Okay, so anyway, we are not going to use this networks because it's tedious. It's using making attempt with the multi-layer. That is making attempt multi-layer because it's tedious for us. Again, if you can do this for us, yes, it is possible. Okay, yes, it is possible. But this network, what will happen? I am sure that this network gives 100% efficiency when compared to single layer multi-layer. Single layer gives, think of it, just 70% efficiency. Multi-layer 80 to 85. That's all. You can able to get only 80% efficiency only. But if you use the feedback formula, you get 100% efficiency. That's the major difference between the different networks, single layer, multi-layer. Okay, but the real-time system, for example, if you are going to make a develop architecture model in the process translation, you are not able to get 100% efficiency. Since we have so many problems on the hardware side, okay, what happens? Yes, we can. I can able to manage 80% efficiency. Yes, we can go with multi-layer. Okay, that's the way. Okay, sir. So the different networks differ from feed-forward architecture, and you can able to find architecture of this like same thing. What we are saying in the multi-layer, you have input layers, then layers, output layers. Am I correct? Okay, and then you can able to find that feed-forward, the same thing. Forward synaptic rates, forward synaptic connections, and if you want to get the weights, what happens? In the multi-layer, what happens? What are the weights here? Am I correct? What are the weights? For example, it is 0.5, 0.6, 0.8, 0.9. If you want to get the defined output, what happens? This will be registered. Am I correct? This will be registered. Am I correct? But here it's not like that. Okay? It will be adjusted. But what happens? The output what you are getting here, in compare to the dot output, and if you find any error, what happens? Again, it will trigger the neurons. Okay, and it is triggered with this neurons. Okay, and for this neurons having some weights, this weights is also adjusted, and parallelly synaptic connections, synaptic weights also adjusted. Okay, synaptic weights also biased. Okay, think of it. Here, in the multi-layer architecture, okay, we are not taking the output. Okay, we are not taking the output of the output layer and act as input in the input layer. Okay, we are not taking. Just what I am saying is one bit output. Yes, try to use the weights here. That's all. Try to use the weights here. And then we increase the neurons in the layers. But here, what happens? This output is fed here. This output is fed here. This output is fed here. And it reaches from here, not from the weights, and reaches from the neurons itself. Okay, that's the thing. But it takes so much time, and the efficiency is still in. And parallelly, if you have monitor, there is no problem, and if still, if it is no problem, and you have input layer, the recurrent network, the feedback network, and parallelly you are incorporating one intermediate layer, this is called hidden layer, and still you are not able to get the efficiency, you have to incorporate another hidden layer. If you incorporate another hidden layer, what happens? That neural network model takes more time to get the efficiency. Again, the neural network model gets more time to get the efficiency. Okay, that's the thing. It takes more time compared to the multi-layer. Okay, that's the thing. We are satisfied with the 80%, not with 100%. Okay. Yes, it should be there, but this type of network is afraid to bring up outline or other spot. Okay. Okay, sir. Coming to next slide. Feedback network or recurrent networks. Okay. The kinetics of the ruling, okay, and murmuring the back side. Please. So single layer recurrent network. And parallel can categorize the recurrent network into different types. First one is single layer and common units. Okay. The single layer what happens? Yes, we have different inputs and we are getting those different outputs. Okay. What happens? That outputs. Okay. What you have seen in the previous slide, that is called a single layer. What happens? Each output layer. You can able to see here. You are getting output, but the output is correlated with this input only and not with this input. Okay. Corresponding output is correlated with the corresponding input only, not correlated with here. Okay. What they are saying? We are trying to adjust here and corresponding to all the weights. Once you adjust the weights, automatically all the weights are adjusted. Here. Okay. And not what I was. This is single one. Okay. How many weights? Yes. As like the weights. Okay. As like here. For example, reciprocated all the things. As like that, the output is reciprocated here and here, here. What happens? It improves efficiency. Okay. Efficiency, yes, it should improve efficiency. Yes. Whatever things you're scoring in that 95, you scored around 96, the same grade. You scored around 90, same grade. Then why you're giving more stress? Why taking more stress to study to take 90 grade? Better can earn 92 or 90 is more than enough. Okay, aspect that same thing here. Feed forward network is that or record network. Okay, yeah, single node network. Okay, yeah, single node network or competing network. The single network, yes, it's that. The feedback is taken and is fed to the corresponding inputs, and not to the all inputs. For example, take the feedback in the loss output. What happens here? You can able to see. All the feedbacks are equal to all inputs, but it's not like that. Okay, and then coming to the single layer record networks. You can able to see figure A indicates a simple record network. And the single neuron will feedback itself. What I said, if you have input layer and if you have the corresponding output layer, the output layer is again fed to the corresponding input layer of the day. Okay, that is called as simple network, simple feedback network. Then coming to the figure C, that indicates that single layer network in feedback from output can be directed to processing element itself or to other processing element. That's the thing. The figure B is elaborate explained here. What happens? Yes, you can able to see mechanic output. Okay, the output is coded to here, here, here. We get the output is coded to here, here, here. We get the output is coded to here, here. For example, we are taking this target. Actually, we are taking two outputs. Okay, it should be like this. Okay, it should be like this one. Okay, I'm parallel getting output. What happens? The output is feed forward here and parallel here and parallel. The output is feed forward here, here, here. Okay, that is called as what happens? Single layer network. What happens? The feedback is conducted to all the processing elements. Feedback is conducted to all the processing elements, the corresponding processing element. All the processing elements. Okay, that is called as the figure A and C. Figure C indicates only the corresponding elements. Figure C indicates the feedback is forwarded to all the processing elements, to all the neurons. Okay, yes. No neurons in output layer is no neurons in output layer is input to the node in the same time processing is called as feed format. That means the feed getting output and output is again not matched to the output. Yes, the output is again taken to the input layer to readjust the weights. If outputs are directed back as input to processing element to the same layer, the processing is called as feedback network. Okay, that's something you are saying. And lateral feedback means if the output are directed back to the input of some other layers. It's called as lateral feedback. This is called as feedback. This is called as lateral feedback. Okay, this is called as single node. Okay, this is called as simple networks. This is called as simple network, but with some complication means yes. The output is directed to all the processing elements. Okay. Today we are not going to use this network. The multi-layers, the same thing. Okay. You can say the same thing. You can able to find all the things. The multi-layer networks, all the processing elements calls for all the layers. Not only processing layer, calls for all the layers. Okay. That is called multi-layers. And leave it this. Okay, sir. So characteristics of neural network. Okay, so characteristics of neural network. What happens? So we are seeing some architectures. Okay, so what's the process? If we take a single structure, single layer, what happens? Yes, you get the output, but you want to get the defined output. Okay, but even though there's a parallel high-speed and distributed information processing, but you're not able to get the defined output. Okay, to overcome that thing, what happens? You are coming for multi-layer. Yes, you can able to improve the efficiency, but still you're not able to fulfill the efficiency. That is, you are not able to get the efficiency 100%. Okay, that is also deals with the parallel high-speed and distributed information processing. We come into this feedback network. Yes, that is the excellent network. Again, you get the 100% efficiency. That is also deals with the parallel high-speed information processing. That's it. Okay, so what happens? You have to select your network depending upon your activities. Okay, what happens? IDP is connectivity among the basic units and weights are modifiable based on the experience. Weights, what an example, getting output between yes. What happens? I'm getting output in of I'm getting if you're putting output between 1, 2, 1, 2, 3, Okay, you are calculating the fault means you are calculating yourself. Okay, 0.9, 0.6, 0.5, but here that should be 1. So that should be error is that. Again you want to rearrange the weights. So in the weights is 0.5, 1, 2 means again I want to relocate it 0.6, 0.9, 2.1. Okay, what happens whether we don't know whether you have to increase or decrease. Whether you want to have to increase or decrease. So we have to make several attempts to fix the weights here. If you fix the weights, let's put it in general. As like that, again you have to check for you. You have to check for you. That is called automatic. Yes, it's possible, but it takes a long time. Okay, that's the thing. Taking your friendly should not be good or high in the outcome. Okay, and finally, unsupervised learning follows. Okay, that means giving the inputs, we are giving the outputs, and fixing the learning technique and fixing the activation function. That's all. What happens? We are not going with an algorithm. Okay, we take our computing, yes, we are using and work, but if you take some computing, it's not needed. Okay, we are not going with algorithm. Okay, sort of it's unsupervised learning process. Teacher will not be there. We have an option. Okay, yes, we give input 9 inputs and 10 outputs. Yes, whatever will get out. Okay, that's the thing I'm going to see in the software, and it possesses the ability to generalize, so they can predict outcome from past trends. That's the major thing. We add some sample sets of reading. Yes, with the sets of reading, we can able to predict something. Yes, it's possible. Again, yes, it's possible. And finally, some fault tolerance system. Some fault tolerance system. Okay, sir. So we have shown algorithms. Okay, what I said in the first slide itself. Back progress algorithm. It is the most important algorithm. Again, the most important algorithm for your engineering application. Okay, hence we have shown algorithm there. The back progress algorithm, best algorithm for the engineering applications, and we are going to see the algorithm. It is founded by Bryson and Chi Wu in 1969, and parallel it is modified in the forthcoming years. Again, by so and so authors. Again, just William et al. And parallel it adds solutions to field of functional principle. For example, they add back propagation, but with some limitations. What I'm saying that each author has his own advantages and limitations. Okay. So if you have a limitation, that will be replaced by the modified by the forthcoming authors. Okay. So okay. What are the back progress algorithm? This is called as backwards propagation of events. Backwards propagation of events. Okay. Check the output. If not there, yes, we are going to relocate the weights to minimize that. Okay. To overcoming there. Okay. Back. Again, I'm going for. Okay. Again, I'm going for placing the weights. Okay. That's called as back propagating efforts. Okay. And it implies errors. Back propagation implies errors. And propagate. What is the word it means? And propagate backwards on the output nodes to the inputs. Okay. It is the nature of the multi-layer architecture. Okay. What I'm saying is multi-layer feed-forward algorithm is nothing. It is called as back propagation algorithm. Okay. So multi-layer feed-forward algorithm is called as back propagation algorithm. What happens? Yes, we are not getting the output. The output, okay, the output will be forward or will be, okay. That is the rearrange the weights until you get the defined output. That is called as back propagation algorithm. Yes. See, you can able to see. BP is used to calculate the gradient of the error of the network with respect to the network's modified weights. Yes, you can able to modify the weights easily. Means you are not going to do, since it's unsupervised learning technique, you are not going to do, but it will automatically adapts, okay, and it gives the results. That's the thing saying that, yes, even though it automatically adapts, it's easy when compared to other network applications. If you take the feedback of the network, it's very tedious when compared to this. Okay, but what will happen if you take the back propagation algorithm, as it's called as multi-layer feed-forward algorithm? What will happen is, yes, whatever you can minimize the errors in several iterations, okay, by modifying the network weights. That means all the weights in the network. Okay. This is the thing I want to see here. Input layer, output layer. You can able to see. In network activation flows in one direction. One link from the input layer to output layer, passing through the 10 layers. This is called as 10 layers, considers input and output layers. Each unit in the layer, input layer or in the layer, output layer, can in the forward direction, not in the backward direction. What I am saying again, I will recall it. It is called as back propagation. called as multi-layer feed forward load. That's the thing we are going to say. Everything in the next slide. Each and everything. Okay? It's like this. This is associated with all the hidden layers. Okay? So the back problem is a multi-layer feed forward network with one layer. Okay, of hidden units or multi-layer of hidden units. Okay? That's the thing we are going to make until back focus on the or multi-layer feed forward. Okay? Okay, sir. So we had some process. We had some process. Okay. So we had several steps of back focus on that. Okay. So what happens? First we have to initialize the weights. Okay. First we have to initialize the weights. That means we have to select the input and we have to feed the input readings, and parallel we have to take output and we have to feed the output readings. Okay. So if you feed the input and output and if you select the learning function, you have to select the network. There will be a multi-layer network or single-layer network. If it's a multi-layer network, okay, no problem. You have to select the training learning tool. You have to select the activation function. That's all. And you click OK and you can wait for 1 hour or 2 hours to get the results. Okay, that's the thing. But these are the stages. You can automatically solve the fitting. You can see the basic steps. Okay, we are not going there. We are going to see only basic steps. Initialization of the weights. That means if you feed the input and output, okay, as 900 samples. For example. Okay, so 70% samples I am fed in the network. That is I am feeding soft computing. Okay, input is that 1, 2 is there. And output 1 and 2 is there. Am I correct? So we are having 100 readings. Okay, you can select any randomly any readings. Let's put 70%. Yeah, 100 means 70 readings. You can select any 70 readings and put it in the software. Okay, and you can select okay, how many inputs, 2 inputs. You have to select 2 inputs. How many outputs? You have to select 2 outputs. Okay, and yes, boss, you can select the hidden layers. So you can select for one hidden layer. One hidden layer means one hidden layer with neurons. For example, I am making an attempt with one hidden layer with 3 neurons. Okay, I am starting this also, and I am selecting and choosing learning neuron activity. That's all. I am choosing learning neuron activity. And I make a trial. Then I ask to take an attempt. I ask to make a run. Again, the math. Yes, you are getting the results. You have to get the results. You are getting the results. That means that network is trained. You are not getting results. That network is trained. And are you going to check the error means, for example, I am remaining 30 readings. Am I correct? I am remaining 30 readings. Take any one reading. Input is 1, 2. Take any one reading. 1, 2. And feed here. Feed in the chain input. Put 1, 2. And again run. You will get the output. Okay? The output. Take here. Compare it. If it gets out as like that, you have to take all the remaining readings, testing readings, and you have to compare it. And if you compare, and you have to compare it, and you have to check the error. If the error is going to increase more than some percentage, what will happen? Again, you have to increase the neurons. Okay? So, what I am saying that you increase the neurons and getting results, and you have to already model is trained. So, you have to test the samples with the trained model. Check it. You have to test the samples with the trained model. Okay? So, after you get the results, that results you have to compare with that results you have to validate with the example, what are the results you are having, and it indicates error. If there is within the limits, yes, you are good. If not, again, you have to go on for searching the product neurons. Once if you train, once if you erase the image, what happens? Once if you bring the function error in the image, yes, this network is perfect. Then you can make an attempt with 102 reading, 104 reading, 106 reading without any. Already I have extreme setup. In the extreme setup, we are taking 70% of readings and making a training and then checking remaining 30 readings. Okay, and testing remaining 30 readings with the trained model. And once the trained model is correct, means what it implies means you already trained and making testing. That testing readings should be coming perfect readings. All the readings should be coming perfect readings. Your trained model is good. If not, means You have to increase the neurons until you get the train, until you get until the error is minimized. Am I correct or not? Understood now? Until the error is minimized. Once you get the exact perfect model, again, there is no need to There's no need to check. There's no need to take the readings of the expert, that is from the setup. Yeah, readings and from the readings you have perfectly designed the model, adopt the model. Then there's no need to take reading again. There's no need to check again. Simply go on to the remaining things, straight to the neural network, and do not make contact with the expert setup, make readings, and then the final reading follow. Better you can check it for your satisfaction. You check it, or the reading should be, most of the readings should be down near to your expert readings. Okay, that's the thing. So initial the rights and feed forward. The feed forward means what actually all the links, all the inputs are forward to the corresponding neurons. Okay, and parallel back propagation errors. Carrying errors, what happens? That errors should be identified. That means errors should be identified by demodifying the weights. Okay, that's called back propagation errors. Once this error is minimized, yes, that is the update. That is the final weight. Okay, and that is the final architecture. What I said. Okay. So last time we were going to discuss the class. The algorithm steps. Yes, we can say. First, we have to initialize the weights. What is in the previous slide. Next, the remaining things are dealing with that. Okay. First, we give the input and output. What are the weights should be assigned? And actually, each input unit receives the input signal X and transmits signal to the layers. What happens? Yes, we have input layers. Okay, am I correct? And parallel we have hidden layers and parallel we have the output layers. Each input associated with all the hidden layers. Whatever the neurons will fix in hidden layers, each input is associated with all the hidden layers. Okay, and parallel the hidden layers associated with all the output layers. Okay, if you have any problem in this output, you have to modify all the weights. Okay, that's the thing. So what happens? That's the thing is saying each input unit receives the input signals. Okay, this input signals, sorry, this is the X input signal X1. And finally, this is what is weights. Am I correct? Am I correct? So this X1 into W is 50 here. Here we have hidden layer. Okay, well, hidden layer H is equal to X1 into W. And parallel we have output layer. O1. Again, O1 is equal to H1 plus this is stuff. H1, sorry, H1 into W2. Okay, that's the thing. You're going to see. So each little layer you will stop switching. For example, for this output, for this thing. For example, for this output layer, getting here. Getting from here. Am I correct? Getting from here. Am I correct? For one feed forward, I have made a calculation. As like that, you will get so many feed forward directions to this corresponding layers. So you have to sum all the contents. That's the thing they say. You have to sum all the contents. Okay? You have to sum all the contents and parallel. You have to apply activation. Plus, what is the activation? The output should be within the linear output. Or whether this is step input or ramp or parallel. Yes. But if you take a notes now, that should be step input, ramp input, parabolic. Am I correct? Understood now? Okay. So we have to fix that. Your output should be linear or parabolic or sigmoid. Yes, we can. That's what the activation function. We can fix it. Okay. And parallel, step 4. Each output unit, each output unit sums weight the input signal. What I mean, that's the thing. But this is not the output weight. Okay. H1 W2 plus H2 into W3 plus the taken from here, it's taken from here, it's taken from here. Okay, so each output unit, you have middle layers, input layer, middle layers, the output layers. Am I correct? So you're getting here, you're getting here, you're getting here, you're getting here. For example, for this number, this W1, W2, and X1, X2. X1, W1 plus X2, W2 was multiplied. And again, this is feed forward here. This is from here, this is feed forward here, from here, feed forward here. This is equal to, you can assume A plus B plus C. That's the thing, that's the process going on. Okay? But what happens? Yes, this is going on. For hidden layer, I have activation function. We have activation function. What happens? You are feeding the input and output. Am I correct? Your output is in the different range. but one output is pressure, another output is temperature, and third output is some other milliseconds. Okay, each output is different range. Okay, so what happens? Whether it's linear or non-linear? You can't non-linear. That's the thing. That's the thing. We are running the activity of this here non-linear. Am I correct? But here output should be linear. That's the thing. For this activity, for interlayer activity is non-linear. For output layer activity is linear. That's the thing. So you have to apply activity function. You have to apply. And finally, yes, you have to check the output. So you are getting the output. Okay, and you have to check the output with the target output. Square answer. That's the thing. Each output unit receives a target pattern. We have some target pattern, and you have to compare it. Okay, and if you have any error, what happens? What happens? If you have any error, again you have to back propagate. Okay, again you have to back propagate to minimize the error. Okay, that's for us. So what happens? You get the target output, and you get the output. The output should be compared, and you have any errors. Yes, the error should be minimized by relocating the weights. Then automatically. Okay? Faster. So, according to step 5, okay, errors calculated and weights are readjusted. What time is it? Yes. You have to compare here, and if you have any error here, and if you have any error in the comparison, yes, you have to readjust the weights. Readjust the weights. How to readjust the weights? How to readjust the weights? It will not adjust the, it will not readjust the weights. Okay, that corresponding architecture will not readjust the weights. That what the architecture model framed in your soft computing, it will not readjust the weights. How are you going to readjust the weights? By increasing the neurons, in the hidden layers. Okay, that's the thing. We have to continue the architecture. You have to continue the architecture until you have to reduce the. How are you going to continue the architecture? How are you going to continue the process? Increase the neurons in the hidden layer. Am I correct? That increase the neurons. You are not going to touch input layer. You are not going to touch output layer. That is a constant. Okay, that is a fixed. But yes, you have the rights to vary the neurons. Vary the neurons in the hidden layer, or you can increase another hidden layer. For example, I make an attempt with 10 neurons. Still not getting results. Good. I make an attempt with 11 neurons. Not getting results. Still that's error. I make an attempt with 12 neurons. Not getting results. Then in order to one hidden layer, okay, most probably 2 neurons can accommodate. One hidden layer, most probably, okay, 2 neurons can be able to accommodate. So going to increase the neurons, better can go for another hidden layer. That is, hidden layer 2 is added for. Okay, so as like that you have to go on going and increase the neurons hidden layer. Not hidden layer is not satisfied. Again you have to jump to other hidden layer. Increase the neurons. That's what now. So 12, one hidden layer, and plus another hidden layer, we make it up to 1, 2, 3, up to 12. Again, if not satisfied, again our hidden layer. Okay, so we have these things we have to done. We have to make an attempt with software. Okay, that's a process called as readjusting the weights, modifying the weights. Okay, readjusting the weights. The software will not reduce the weights plus. We have to reduce the weights. Yes, we have to increase the neurons hidden layer, or we have to increase the another hidden layer. Okay, then only the weights will be registered. Okay, last testing the stop. Testing the stop. If the error is minimized by adjusting the weights, okay, yes, we will get the final decision. That is, you have to stop. Once the error is minimized, you have to go for final decision. That's all. And what the error is not that. That is the network. That is your Paka network. That is your exact, perfect network. Okay. So for that getting perfect network only, we are going for training the neurons. Okay. That's the called as back propagation of the network. This is known as multi-layer feed-forward network. Okay. Okay, sir. Next, last slide. So we come into robotics. For example, that's about robotics. Anyway, I'm not going to. Okay, just we can say our case today. That's all. I can able to finish this last. This is the last slide. Okay. So this one of the sensor robotic. You can think it's a robot. Okay. And parallel, you have 3 sensors. Sensor 1, sensor 2, sensor 3, and motor A and motor C. Okay. Motor A moves forward or back or C. Motor A is forward or indicates backward, or C indicates forward or backward. Whatever it may be. Okay. So what happens? The back propulsion network has to be modeled for our robot. So from the robot has 3 inputs. Yes, Output sensor 1, 2, 3. Two touch sensors and one light sensors. Okay, and two outputs, that is motor A and motor C. And we are proposing the 3-layer back propagation network. That is something called multi-layer feed-forward network. And value one is the input layer, 3 inputs and 2 outputs. Going and increasing, touching the performance. First one. So this is a bell layer. Here we are having 3 neurons. Okay, first you have to make 1 neurons. If not satisfied, you go for second. Not satisfied, go for 3. Okay, so in this case study, you make an attempt with 3 neurons to minimize error. Okay, for example, so moving forward, what will happen? Sensor 1 will activate and sensor 2 and sensor 3 will be off. For example, this is considerations considered for training the neural network. Okay, so moving forward, sensor 1 is off and sensor 2 and sensor 3 is off. Then only you can see motor A and C go forward. Motor direct to simultaneous motors, it goes to the forward direction. Okay, and if you have to move the right, you have to move the robot right, means what happens? Sensor 1 should be on and sensor should be on, motor A goes forward and motor C goes back. Okay, moving left, and leave the next slide, it is clearly. Yes. Just think of it. So rules to learn. Sensor 1, we have 4 rules. Sensor 1 should be off. Sensor 2 should be white. That means white means 0 or 1. Okay. White means you can consider it on. Black means you consider 0. Okay. Off means 0. And think of it. White means 0 and sensor 3 means off means 0. 0, 0, 0. Okay. Black means 1. Okay. You can think out sensor white means off. Sensor 1, 2, 3 white off means yes forward. Not A and C forward. Sensor 1 on and sensor 2 is off and sensor 3 is off means forward and backward. All sensors on condition, both the motors moves in forward direction. Again, first sensor is on and remaining sensor off means yes goes motor A moves forward, motor C moves backward. And coming to sensor 1, the rule, sensor 1 is off, sensor 2 is off, and sensor 3 is on means yes. We can able to get A is backward, that's inverse of second rule, backward and motor C is forward. Coming to the fourth rule, okay, sensor 1 is off and sensor 3 is off and sensor 2 is only on. What happens? Both of backward directions. Okay, so for example, this is a contagious. Okay, if you forward this structure, okay, this tool in the matter of sociology, the neural network, yes, you can able to predict. For example, okay, here we have the 0, 0, 1. If it is 0.5, that's our blinks partially and not blinks partially. The blinks are you can able to see. Light, okay, what happens to 10 minutes too clear, 15 minutes DMX. Okay, what happens? Whether you cannot able to say it's off or on. That's the thing you're going to decide. Okay, that neural network you have to decide. That if it's a 0.6, for example, you can take a bit 0, 0, 0, 1, 0, 1, 0, 1, resolve 0, 0, 0, 1, 2, 1, 2, 3. For example, I am locating in 0.5, 1.2, 2.3. I am able to say, so if you are having one rule, 0, 1, 2, this means log means 1, 2, 3 means 1.5 indicates, yes, you can able to say so. If you are having 3 inputs, you have to compare 3 inputs and you have to say, this is final truth. It's not possible. Okay, that's the thing. For example, here 0.5, here 1.2, here 2.3. What do you mean? You have to compare with each and every input. Then you have to find a thing. Okay, that's the thing is going to okay. Last one is. Okay, sir. You can write the phrase here. Okay. Within that, there is the older students and the new students, 8 years students. Okay, sir. Shiva, getting up to that. So, we're going to see the neural network. Okay, basics models of neural network. Okay, so we have several models of neural networks. Okay, A is for artificial neural network. We have the models of neural network. The neural network is here to check the performance or to predict the readings. That is to predict the performance. Okay. This is some sample of ratings. Okay, so what are models available in neural network is basic models are three entities. Okay, model synaptic interconnections, training or learning rules, one of them for updating and adjusting the connection weights, and their activation function. Okay, so last class itself we are discussing this what is the activation function, and parallel we are seeing the inputs. Okay, we are seeing the inputs. Okay, we have the neurons like this. Okay, each neurons they are having some weights W1, W2, W3, and parallel it is interconnected here. That is called as axon. Okay, that is called as sum. You have to sum it, and parallel you have to get the output. That is called as Y. Okay, in the output we have some function is called as activation function. Okay, that means some triggering function is that. Okay, so that output will matches the output. What are outputs coming? We have to compare with activation function. That means the output is comparing the trigger with the activation function, and if you get out, if it is okay means yes, you get the defined output. If not means you get the undefined output. Okay, that's the thing we are going to see here. So the model synaptic interconnections. That means the model synaptic. This is called as architecture. This is called as architecture of A. Okay, so we have the models like original model, A1 model. So the synaptic interconnection means what? The synaptic interconnection means that means what is by synaptic. This is called as synaptic interconnection. This is called as, in terms of biological side, we call as synapse or synaptic. Okay, synaptic fluid or synapse fluid. Okay, so this is called as synaptic fluid with respect to one parameter. This is called as synaptic weights. Okay, or synaptic interconnections with respect to weight other parameter 2. This is called as synaptic connection with respect to parameter 3. Okay, so what happens? This is called as synaptic functions, and partly the training or learning rules. Okay, in order for updating and adjusting the connection weights. For example, yes, giving the synaptic weights and getting the output. If the output is not there, for example, the output is coming as 8, but dash should be. Okay, dash should be. Okay, output is 8.5. What happens? What are the outputs getting from the neural network model is not matching with that. Okay, our target output. It's not matching with our target output. Okay, what happens? Yes, you have to leave this thing. Otherwise, you have to get the output is 8.5. For that, again, you have to readjust the weights. What I am saying that yes, last class was saying that I'm taking the class here. I'm focusing outside of the weights. I have to concentrate the class. Okay, I have to do the class. I have to take the class around 85% means yes, we are taking the class. And it's not but we are following the neural model and checking that whether my FCT is around 80% or not. If it's just 82%, again, what happens? Again, I want to restructure the weights. Again, I want to restructure synaptic interconnections. But things like here. Again, what happens? Then I want to give more concentration. Okay, I want to exhibit more weights and comparing to that weight. That means I have to reduce the weights, I have to reduce the synaptic interconnections to that side, and I have to increase the synaptic interconnections with respect to my side. Then only I can able to do, and then only I can able to achieve 82% efficiency. Okay, that's the thing. Yeah, what the output is getting. Okay, even though it's compared to activation function, what output is getting, that should be matched to the target output. If not, means again you have to relocate the weights. Okay, that's the thing he's saying. And by the activation functions, okay, that's called threshold function. The training are learning rules, what are for updating and adjusting the connection weights. What example? Yes. For example, I want to reduce the weights. This is possible. For that, we are several learning algorithms are there. For example, back propagation. Back propagation algorithm is there. Second one is to take the EM. Third one is X1, X3, as that we have several algorithms are there. Okay, what happens? We have to select, for example, yes, if you don't get the efficiency, I want to improve the efficiency by adjusting or relocating the weights. Yes, then we have to go for a back propagation algorithm. That is, we have to readjust and correlate the weights. Okay, so as like that, we have to select the learning group. That is, activation function is different, synaptic interconnection is different, and training the learning rules are other. Okay, training the learning rules means yes, there are several rules. Okay, for readjusting the weights, we have to select for each of the weights we have around 5 or 6 routes. Okay, so we have to adopt each and every route in this numeric model, and you have to find out which training is the which learning rule is best for your model. For example, I am having around x1, x2 up to x100. I am having 100 learning rules. Okay, but I have to relocate if I am not getting the defined efficiency, defined output. Yes, I have to relocate the weights again. Then what happens? For relocating the weights, there should be around 10 learning rules or 5 learning rules. Thus, we consider 5 learning rules. Okay, x1, x2, x3, x3, x4 in the different form, in the different names. For example, x1 is Leeuwenhoek. Okay, L1 means Leeuwenhoek argument. That's one of author. Okay, and finally you can able to do a scale conjugate. Scale conjugate. That's also one of the training rule. SCG. You can say it all as SGC. SCG. Okay, as like that we are several learning so that these are rules adopted only for relocating the weights. Okay, relocating the weights. Okay, so what happens if I want to relocate the weights? We have to adopt this rule. And finally we are in 5 rules. Okay, what happens? We have to adopt. Okay, we have to justify which rule is best among these 5 rules. Is it possible? Yes. We have to fix each and every rule. We have to adopt each and every rule in the training network, and we have to find out. Okay, and you have to find out whether it is defined out or not. Okay, if not means it's a problem. Okay. Okay, sir. So what happens? The arrangement of neurons to form layers, the connection pattern forms between the layers called as network architecture. What happens? Yes, we are input layers. Okay, we have input layers, we have output layers, and we have some layers, including input and output layers. Okay, that's called as network architecture. That's called as a combination of all the layers is called as a network. We can say the architecture of the neural network. Okay, architecture of ANN model. What happens? Yes, we are in 5 architectures. We are in 5 types. Okay, we can categorize into 5 types. First one is single layer feed-forward network. Okay, single layer feed-forward network, and multi-layer feed-forward network, and single node with its own feedback. And fourth one is single layer recurrent network and multi-layer recurrent network. Okay, so we have 5 types: single layer feed-forward, multi-layer feed-forward, single node with its own feedback, single layer recurrent network, and multi-layer recurrent network. Okay, so what happens? Yes. First we are going to see the single layer. Before going to single layer neural network, first we can see the neural network architecture. That is known as ANN architecture. How it happens? Okay, how the architecture should be. Okay, if you want to train the model, how the architecture should be. Okay, for your model. Okay, you have to think of it. So what happens? Yes. So what happens? Yes, behind the neurons. Okay, and parallel there is synaptic connections here. That means yes, E1, E2, E5, E4, E3, all the synaptic connections. Okay, so and parallel we can say the vertices means is called as neurons. That is one of the functioning unit that's called as neurons. And parallel edges E1, E2, E3 is called as this is called as weights. Okay, so that is called as synaptic weights. What I am saying that logic neuron is a data processing system consisting of large number of simple highly interconnected processing element as artificial neuron network structure that can be indicated using a graph G. Okay, yes, there is a graph which indicates a G. That is neural network architecture. Okay, this is called as graph G. Okay, if you come from basic side, you have to learn this. Okay, anyway, this is called as graph G. Okay, in that graph G, we have vertices and edges. Okay, edges means here the considered as weights. Okay, edges is called as synaptic links. Synaptic links. That means the links between the one neuron and second neuron. Okay, that is we are carrying the synaptic links to transfer the weights from one neuron to next neuron. Okay, that is called as synaptic links. And the vertices means the exact neurons. For example, this one of the neurons, this one of the neurons. We can consider it from the vertices V1 to V2. Okay, we have synaptic weights, synaptic links for V5. V5 will transfer this input with the weights to here. Okay, and parallel V4, what will happen to get the synaptic links? Okay, V4 and parallel we have the neurons. The neurons, what you can think of it? The input of neurons will depend upon the V2 neurons and parallel to the weights. Okay, as like that. This is one of the sample architecture. Okay. This organization indicates a new network architecture. And well, yes, we're going to the types of a single layer feed forward network. Single layer feed forward network. What is by single layer feed forward network? Why it is called a single layer feed forward network? Single layer feed forward means just we have two layers. Yes, we have two layers. Again, what are the two layers? This is called this left side is called direct indicates input layer and this green indicates output layer. Then since we have two layers, how it is called a single layer? Can you able to justify? Okay, what I'm saying is single layer is here. What will happen? Single layer is yes, this single layer is input output can consist of. Okay, we have input for the input and getting output. Am I correct? Okay, so that is called a single layer architecture. Okay, so what happens if we add more number of layers in the intermediate to this side? If you are having a chance, yes, it should be there. You can able to increase you can increase your layers as like this. Here in between the input and output. Okay, it's not possible before the input and it's not possible before the output. Yes, it can possible. Why you are going for adding that one more layer? That is one more intermediate layer in between the input and outputs. Yes, we are going to see in the next coming slide. What I meant to say is, yes, the single layer feed forward mechanism here the architecture is able to display right input layer. Okay, we have different inputs and then we have different outputs. Okay, and parallel we are able to say each input is associated with. You can able to find out each neuron. For example, this is negative. This one you can see the vertices of neurons. What happens? This neuron is negative this neuron and parallel this neuron and this neuron. And if you take neuron to X2 input is associated with this output, and this output. Because each and every output is having relation with each input. Okay, so you cannot be able to be, for example, this input is related with this output. It's not possible. Okay, so what happens? This input is related with these outputs, and for this input with this outputs, and for this output is related with this output. Okay, we have two. Okay, we have to correlate. We have to correlate all the inputs with the several outputs. Okay, that's the thing. You can able to get a different output. For example, I'm considering only this input, this output, this output, this output. Yes, it's not possible. You're not able to get the defined output. Yes, I'm considering for this input for 2 or 3 outputs. It's not possible. What I'm saying that we have to correlate all the inputs with all the defined outputs. Then only can able to get what I'm saying that then only can able to get the defined. That means what the target output. Okay, then only can able to get the defined output. Okay, then you have to compare the defined output with the target output. Okay, that's the thing. You have to correlate all the things. Okay, yes, single layer feed forward means why it's called a single layer. Okay, it consists of input output layer is called a single layer. What is the feed forward? That's only actually in the forward direction, not in the reverse direction. You are not having the feedback system. Okay, what I mean is we are going to let the output. Finally, get the output is here. Am I correct? Output is here. Okay, what happens? My target output is 9, but I am getting the output is 8.5. Okay, you can leave the side, getting the input, and what are things going. They will see the detail in the following slide. And finally, getting the output is 8.5. What should be your target output is 9? Target output is 9. What happens? What is the general rule? What I said in the previous slide. You have to reallocate the weights. Am I correct? You have to readjust the weights. So what happens? Here weight is 0.5. If I increase 0.8, what happens? Parallelly, that is called neural network is called a simultaneous process. Parallelly, here weight is actually weight is here is 0.7, this is 0.6, this is 0.5, 0.4. If you adjust one weight, okay, if you adjust one weight, what happens? Yes, we'll be able to get the different output here. Okay, but that weights will have correlation with other output, one output. What happens? What are the output? For example, if you get the different output here, that output will be increased or decreased. Okay, so once it reaches the weights, we have to readjust all the weights, okay, within the associated layers. Okay, so yes, it's possible. Why is that? It's not possible in our computing. Yes, it's possible. But if you have 3 input layers and 5 output layers, if the input is going and increasing, the output is going and increasing. For example, if I have 10 input parameters and 40 output parameters, so it's possible in our computing.